Okay, this video is about parity, part 3. And I'm going to start by reviewing some of the things that we've done in the previous two videos. The first thing is a permutation is even if its inversion number is even, and a permutation is odd if its inversion number is odd. And the inversion number for the identity permutation is 0 because there are no inversions in it, and hence E is an even permutation. And finally, the last video, we proved that if gamma is a 2-cycle, and well, actually, it was 2 videos ago that we proved that if gamma is a 2-cycle, then the inversion number of gamma is 2 times b minus a minus 1 plus a 1, and this 1 means that the parity of every transposition is odd, and so all transpositions are odd permutations. The last video, we proved what can be called the Parity Lemma, and it's if alpha is any permutation in Sn and we take a transposition, then it turns out that the permutation that we started with and the permutation first do alpha then do gamma have opposite parity. One of them has an even inversion number and one of them has an odd inversion number. We don't actually know which one is which. There's one other thing that I also want to review, and that's that I think it was 2 videos ago that we showed that any permutation can be written as a product of transpositions. And this basically follows from the fact that any cycle can be written as a product of transpositions, and any permutation can be written as a product of disjoint cycles. But it is important to note that the product of this kind of a product is not unique. And so the fact that that product is not unique brings to the forefront the following question, which is, if I have 2 ways to write a particular permutation as a product of 2 cycles, what can I say about them? And one thing that I want to notice is that I can't even necessarily say that the number of 2 cycles in the product is the same. And but it does turn out that there are several things that we can say about that, and that's what we want to investigate in this particular video. So let's go on. So our starting point is going to be that we have alpha is just anything inside Sn, and we know that alpha can be written as, say, gamma 1, gamma 2, all the way up to gamma k. Now I'm actually going to ask a different question first, and let's make that subscript just a little bit easier. The first question that I'm going to say is, what can we actually say about alpha right now in terms of its inversion number? And it turns out that this is not a difficult question to be looking at. What we know is that the inversion number of alpha 1 is odd, so alpha 1 is an odd permutation. And we know that if we compose alpha 1 with another transposition, named alpha 2, the parity changes. So this guy has to be even. Now, that's a perfectly good permutation itself. So if we take that even permutation and we compose it with another transposition, the result has to be an odd permutation. Well, if I take that one and I compose it with another transposition, the parity has to change from odd to even. Well, you keep doing this and you realize that the parity of alpha has to be the parity of the integer k. In other words, if k is even, alpha is even. And if k is odd, alpha is odd. And that's the first thing that we want to be thinking of. Now, one thing that is going to come back in a few minutes is we know something about cycles, but we're going to look at that in just a minute. This fact here, that if I have alpha written as a product of two cycles, that will say that alpha is even if and only if k is even and alpha is odd if and only if k is odd, has some really important consequences. And let's look at one consequence in the next slide. So here we're going to assume that alpha can be written as gamma 1, gamma 2, composed all the way up with gamma k, and alpha can also be written as delta 1, delta 2, all the way up to delta L. And these are both products of two cycles. Now, what I want to notice here is that the inversion number of alpha, that's sloppy, so the inversion number of alpha is well defined. Let's see if I can get my pad in a place where the writing will be neater. So what I know is that the inversion number of alpha is well defined. And what I mean by that is that if we have alpha as two-row notation, and the bottom row is I1, I2, I3, all the way up to In, there is a fixed, specified number of inversions. In other words, there aren't two ways of defining this inversion number. No matter how you look at the two-row notation, when you untangle it and the top row is in order, so the top row is in order, you count the inversions down here, so you count the inversions on that second row, and that gives you the inversion number of alpha. Well, that means the parity of alpha is well defined. So let's see. That says the parity of alpha is well defined. And that's going to be critically important when we come back up to looking at this particular product. So let's go to the next page. And we're going to rewrite that alpha is equal to gamma 1 followed by gamma 2 all the way up to gamma k. But it's also equal to delta 1, delta 2 all the way up to delta L. Now, the parity lemma and the stuff that we just finished a few minutes ago, so the earlier stuff, let's call it that, together these things imply that the inversion number of alpha has the same parity as k. But the parity lemma and that earlier stuff also imply that the inversion number of alpha has the same parity as L. Well, what this means is that the inversion number of alpha and K are both odd, or they're both even. And likewise, the inversion number of alpha and L are both odd, or they are both even. Now, the inversion number of alpha doesn't change. This is the same in both statements. It's the same integer. And so what that means is that if this number, if the inversion number of alpha is even, then both K and L are even. And it also means that if the inversion number of alpha is odd, both K and L have to be odd. So what does that say? That says these two numbers here have the same parity. K and L have the same parity. And what that means is that any way to write alpha as a product of two cycles has the same parity. Now, what I mean by that is this. If our permutation is even, and if alpha is written, that's very messy. If alpha is written as gamma 1, gamma 2, all the way up to gamma k, that is any product of two cycles, then the number of two cycles in the product is even. And likewise, if alpha is odd, and we write alpha is equal to, say, delta 1, delta 2, down to delta L, and this is a product of two cycles, then what I know is that the number of two cycles is odd. And this particular result is usually referred to as the parity theorem. And just to state the parity theorem more carefully, the parity theorem basically says the following. Let's write that with a better Y. So the parity theorem can be cleaned up as follows. If alpha belongs to Sn and alpha is equal to gamma 1, gamma 2, all the way up to gamma k, and it's also equal to delta 1, delta 2, all the way up to delta L, where all of the gammas and all of the deltas are 2 cycles, then K and L both have the same parity as alpha does. And what that means in English is that any particular product of alpha broken down into 2 cycles is going to either have an even number of 2 cycles or an odd number of 2 cycles. And that is it for this particular video.